Thank you, Don, for that introduction. It's too kind, most kind. It's a great pleasure to be here in the PM at what used to be the Pear Marquette and now is the Peoria Marriott. I'm, of course, in the PM of my life. But like all the speakers, I sent in a proposal to speak at this year's ICTM meeting. I picked a topic that I felt would be appropriate for a session at a particular grade level. My proposed topic was hierarchies. Then the program organizers told me they would like my talk to be the closing session at the meeting. I realized that hierarchies was not a general enough appeal. What should I do? One possibility was to make my talk more general. Hierarchies and lowerarchies. Or hierarchies and bierarchies. Or hierarchies and soberarchies. You can see that this was not going in the right direction. So I decided instead to change the topic entirely and speak about the Common Core state standards in mathematics. After discussing the purposes of this talk and the rationales for it, the talk has 4 parts. The first part deals with the current scene and what got us here. The second part with the changes needed in the process of creating a next edition of the standards. The third deals with changes needed in the substance of the standards. And the fourth part deals with changes needed in the testing. Since the testing is not yet finalized, it's possible that those of us who are making suggestions for change may be able to influence what will happen even next year and the next couple of years. My purpose is to replicate something that I did in November 1992 at the University of Chicago and at the annual NCTM meeting in April of 1993, 20 years ago. On those occasions, I gave a talk titled, "What Changes Need to be Made for the Second Edition of the NCTM Standards?" My first motivation for that talk was obvious. I felt that some changes were needed. But my second and equally important motivation was that no one was talking about when a major rethinking of the standards, of the NCTM standards, would be appropriate. And I felt that maybe a talk on the subject would help get the ball rolling. It did. And it led 7 years later to NCTM's Principles and Standards for School Mathematics of 2000. That same motivation drives me today. I think changes are needed in the Common Core, but no one is talking about when we're going to rethink the Common Core, and I think it's not too early to get the ball rolling. Not everyone is on the Common Core bandwagon. That would be too much to expect. A movement as large as this one will always draw opposition. The loudest single voice has come from Diane Ravitch. But there are many other voices. In Alabama and Indiana, the legislatures have debated seceding from the Common Core movement. And I read this week that 6 states have withdrawn from the PARCC consortium, although Steve Leinwan says it's not, they haven't officially withdrawn. I was told by Uri Treisman, a well-known math educator from Texas who heads the Dana Center, which is developing test items for PARCC, that there is organized opposition on general grounds in almost every state in both language arts and mathematics. Some are opposed because of the content of the Common Core, some because of the loss of local control, some because of the lack of flexibility, some because of the testing, some because of the cost in time and money, and some because they foresee huge numbers of students failing the Common Core tests, being held back, and leaving school, whereas without the test they would remain in school. My purpose today is not to discuss the various sides on this issue, but I did want you to realize that there are reasonable people opposed to the Common Core. And when the more vocal criticism comes, and it will come when the test results come in, it will be useful to have thought already about what changes might be made. The currency. To understand the process of doing a revision of the standards, it helps to understand what led to the Common Core. The first event that can be said to have led to the Common Core was the appearance of the NCTM Curriculum and Evaluation Standards of 1989. These standards set a precedent for national standards in a subject matter field, and their authenticity for setting national goals was established when NSF decided in the early 1990s to fund a variety of curriculum development projects at elementary, middle, and high school to explore ways of implementing the standards. This gave the first purpose of standards to set goals, national goals for the curriculum. And this is the first purpose of the Common Core. The second event leading to the Common Core was the appearance of a splintered vision in 1996 as part of the Third International Mathematics and Science Study, TIMSS. The authors of this document argued that a major reason our mean score was behind other nations on TIMSS was due to the lack of a consistent vision across the nation. This gave the second and third purposes of today's Common Core: to bring the U.S. score on international assessments up to that of the highest countries of the world, and to do this by having a common curriculum for all students in the country and high-stakes testing to ensure that the curriculum gets to the students. The third event, at about the same time, was the entry of some mathematicians expressing the view that a major reason for low scores in California and other states on national assessment was the NCTM standards and the curricula based on them. Never mind that in 1996 these curricula had not really been used anywhere. These mathematicians saw greater numbers of students taking what are called remedial mathematics courses in college, and greater numbers of foreign students in their graduate courses, and no greater numbers of students majoring in mathematics, despite the assertions of so many that mathematics is as important as ever in our technological age. They argued against what they called the fuzzy math of the NCTM standards and the constructivism that was fostered in the NCTM professional teaching standards that had appeared in 1991. This gave two more reasons for today's Common Core: to eliminate the impact of the NCTM standards and the NSF curricula based on them, and to replace that curriculum with one designed to prepare mathematics majors. Fourth was the No Child Left Behind legislation of 2001 that established the U.S. Department of Education's entry into the scene. It set annual testing of schools and penalties for low-performing schools. This gave us two more reasons for the Common Core: to close the achievement gap between blacks and whites and between Hispanics and whites, and to improve teaching by using test scores to get rid of low-performing teachers. Finally, the Common Core were pitched to states during a time of a recession, when states were looking for ways to reduce their budgets, and states hoped that by joining together to create standards and assessments of those standards, better results could be obtained for less money. The logic is compelling. Get the best people in the nation in a room, give them the task, and the result will be better and the process less costly than if 50 groups of people get together in 50 rooms for the same reason. Now, let me talk about the changes needed in the process. A splintered vision begins with the following statement. You can read it. Can you read it in the back? Oh. Did you say no? No. So, I, who have learned, was good at language arts as well as mathematics, shall read it for you. There is no one at the helm of U.S. mathematics and science education. In truth, there is no one helm. No single coherent vision of how to educate today's children dominates U.S. educational practice in either science or mathematics. There is no single commonly accepted place to turn to for such visions. The visions that shape U.S. mathematics education are splintered. This is seen in what is to be planned, to be taught, what is in textbooks, and what teachers teach. The thesis of this argument of Bill Schmidt, Curtis McKnight, and Senta Raisin was that a major reason for our mean score being behind other nations was due to the lack of a consistent vision across the nation. It's interesting that earlier this year, I heard at a meeting of the Metropolitan Math Club of Chicago, Phil Darrow, one of the 3 writers of the Common Core, say that there is no one in charge of the Common Core. The work group appointed to develop the Common Core Committee no longer exists. The 3 authors, Phil himself, Bill McCallum, and Jason Zimba, have no official capacity. There is no organization in charge. Not the National Governors Association, not the Council of Chief State School Officers, not Achieve, not NCTM, nor any other mathematics or mathematics education organization. No change can be made at present in the Common Core because no person or organization has the responsibility. Phil Darrow said, quote, "It's not clear who the next people will be, not even clear who will organize it," end quote. The problem with having no one responsible for the Common Core is that no one is accountable. So we have a situation in which every student, teacher, and public school in grades 3 through 11 is being held accountable for mathematics performance under guidelines for whose preparation no one is accountable. You might argue that the individual states are accountable, and to a degree they are accountable if they made changes in the Common Core. But it's hard to call them accountable if, like Illinois, they merely have accepted the Common Core as is. They can simply say, we did not make the rules, we are simply going by the rules. That is not accountability, because there is no one to take the blame for the rules. This must change for any next version, and I believe that we in mathematics education must take back the leadership for school mathematics that has been wrested from us by entities that either have no members or are political rather than educational in nature. The natural organization to take the leadership is NCTM, but it may be appropriate for NCSM to do what it did 35 years ago, when it came out with its position paper on basic mathematical skills and jump-started the process of extricating us from the Back to Basics movement. By the way, we have a person from Illinois running for president of NCSM, Steve Victoria, and if you, I think, and if you want, you should vote for him. Is that enough, Steve? Did I say enough? I hope that the leaders of ICTM badger these national organizations to take back the leadership in mathematics education. We have another natural voice since Diane Bryers, the next president of NCTM, is originally from Illinois. One of the early complaints about the Common Core was that the work group did not have enough time to do its work and gave only about a month at the very end, actually 22 days, for outside comments on the document, far too late for any significant criticisms to be accommodated. One of the major points made by Diane Ravitch and others is that over 40 states have adopted a curriculum that has never been tested by anyone, anywhere. Indeed, most of the states that adopted the standards did so before they even appeared. How's that? So any timeline for a second edition of the Common Core should allow enough time for development, public comment, revision, testing of the new ideas, and lead time before implementation. In Japan, for a number of decades, there's been a planned revision of the curriculum every 10 years. I use Japan as an example because their system for changing curriculum is the most refined that's known to me. They call their document the course of study. It takes 2 or 3 years for the course of study to be implemented. It is not implemented all in 1 year. For instance, the current course of study in Japan was made public in March of 2008 and was implemented fully in April of 2011, 3 years. The Japanese school year starts at the beginning of April. That's why those months. 2 years after implementation, when there have been some results of student testing, a committee meets and makes suggestions for the next course of study. This is 5 years before the next course of study goes into effect. These suggestions are let out for public debate, and then the final document, a revised course of study, appears about 2 years before its required implementation to give time for teachers to be trained in whatever is new. The U.S. is not so organized. Some places began teaching the Common Core this year, so that the testing in 2014-15 will be the third, they began testing this year, so it'll be the second year only. Some places began last year, so it'll be the third year, and some places I know haven't yet started. In general, however, I think people have been satisfied with the amount of lead time for implementation and training. We've had a couple of years. We will have 2 years of test results then by June of 2016, so a committee could begin meeting then and possibly come out with revised standards in a year, give a year for debate and modification, and then 2 years for implementation, so that in 2020 there would be a new version of the standards. So I think the goal should be for revised standards in 2020. You might say, I have 2020 vision. If you expect a change to work on a large scale, you need to try it out at least on a small scale. Not only was this aspect of the Common Core completely neglected, but in the present implementation of the Common Core, there is no place for trying out new ideas because all students in all public schools in the population are being tested. You might argue that we could test in private schools, but those schools are special in that they don't have to accept all students, a luxury not available to the public schools. And many of them, if not most, are accredited by their states, and they're subject to the same Common Core testing because of their accreditation as the public schools. The difficulty of trying out new ideas is a huge problem associated with the Common Core. President Obama repeatedly calls for innovation, but the Common Core stifles innovation among our teachers, and where else are our students expected to learn to innovate, if not from their teachers? In April of this year, the U.S. Department of Education launched a 2013 Investing in Innovation competition. There are 8 priority categories for innovation, including one called Improving STEM Education, which does not have to do with flowers and trees. It's STEM education, you know, science, technology, engineering, mathematics. But I don't see how a school can afford to risk adopting a new curriculum if its students are going to be tested on the Common Core. Japan has a built-in mechanism for trying out its new ideas. It's schools that are affiliated with its teacher training universities. In March of this year, I was at 2 of these universities. Each has about a dozen affiliated schools. These are the places in which prospective teachers do their student teaching and in which ideas such as lesson study have been honed. We have no such mechanism built into our system. We need to develop a mechanism immediately by which a school can petition to implement a curriculum different from the Common Core. Obviously, the standards should be written by knowledgeable people. But what knowledge? The people who write the standards should be experts in curriculum, in various ways in which each mathematical idea can be developed, how the development can be modified for different populations, and how much time is reasonable for the ideas to be learned and applied. The writers should have experience teaching students at the levels for which they write. Some should be aware of the mathematics curricula of other countries, and many should be aware of the latest developments in curriculum. And they should have experience writing materials for students so that they're aware of the choices, difficulties, and subtleties of organizing and sequencing content for optimal learning. Sadly, that was not the case with the Common Core. For instance, there is the document titled K-8 Publishers' Criteria for the Common Core Standards for Mathematics, which has the logos of the National Governors Association, the Council of Chief State School Officers, Achieve, the Council of Great City Schools, and the National Association of State Boards of Education. The first version of this document, the Publishers' Criteria, appeared in the summer of 2012. That version, I've been told, was written by one person and never vetted beyond a few people, but was immediately applied in some places, both states and by publishers, as if it was the Ten Commandments from Mount Sinai. Note quite significantly that there's not one mathematics education or mathematics organization involved, nor is even the Association of American Publishers involved. So the people who know the most about the development and implementation of curricula were not part of the process. In April of this year, a second version appeared. The second version has the same logos. But to indicate how out of touch the writer or writers were, I wish to comment on a paragraph in the original document. The 9th of 9 indicators of quality in instructional materials and tools for mathematics. And here it's quoted. For paper-based materials, a textbook that is focused is short. For example, by design, Japanese textbooks have less than 1 page per lesson. Elementary textbooks should be less than 200 pages, middle and secondary less than 500 pages. Some of you find this humorous? This will do for September, right? Okay. In the second version, this paragraph has been deleted. But I'm going to talk about it anyway. Because it caused fits for those who write mathematics materials and caused great damage because a publisher cannot just create some materials and then create others when the whim of a writer changes. Do the Japanese textbooks have less than 1 page per lesson? Here's the number of pages in each grade of a current Japanese series for grades 1 to 6 that has been translated into English page for page. I could not find any lesson in any of these books that is less than a page in length. There are not many problems or exercises in these books, so I wrote the Japanese professor of mathematics education who headed the translation and asked him about that. He wrote back that, quote, all students are to buy auxiliary materials such as worksheets and exercise book, which correspond to the textbook page by page. They look quite the same as the textbook. So the actual number of pages the Japanese students are required to encounter in the mathematics year is over 500, about the same length as textbooks from the major publishers in the United States. In short, all of this stuff about the length of books in other countries seems to be a crock. Because unlike U.S. books, the books in other countries don't serve the purpose of containing all the questions and practice problems that students are required to encounter. So the statement in the original publisher's criteria was false, and the use of that statement as the justification for telling publishers that their books should have less than 200 pages is an outlandish recommendation, a crime. Jason Zimba, one of the authors of the Common Core, was asked by a reporter for Education Week about the decision to delete this paragraph. He's quoted as saying, that, and I have the quote here, that was the last bullet point in the document. As if, I put it last so nobody would really read it. And attracted an awful lot of comment. That bullet point was doing more harm than good, but I'm glad we started the conversation. The publisher's criteria document did not start the conversation. The conversation was started in 1987, when Jim Flanders published a paper in the Arithmetic Teacher about the amount of review in elementary school textbooks, and naming the 3 major series that he examined. Publishers immediately responded by cutting down the review. The conversation was continued in the NCTM Standards and by the projects that were funded by the National Science Foundation. The Common Core writers did not start the conversation. They attempted to end it with an ignorant and outlandish recommendation. But I do not want to let mathematics educators off easy. There are a number of researchers in this country who are fluent in Japanese and are familiar with mathematics education in Japan. some because they were educated in Japan. They've done our profession a disservice by not immediately pointing out the falseness of this statement about Japanese education. The creation of standards is a very difficult task. We learn from this that any revised standards and the explanatory material that accompanies them should be written by people who specialize in mathematics curriculum, that is, by our most gifted teachers, supervisors, authors, and professors in mathematics education, not by people in related fields, regardless of how smart they might be. The authors need to be aware of the possible consequences of their decisions, both intended and unintended. This is more justification for the leadership in a next edition being held by NCTM and NCSM. So now let me turn to what you might find most interesting, changes in the substance of this. We know the Common Core was quickly written and let out for only 22 days for public comment. It's to be expected that the Common Core contains some major errors in judgment. I can't give detailed thoughts regarding the 8 standards for mathematical practice and the 385 standards for mathematical content in an hour. Maybe 62 minutes, but certainly not in an hour, or actually not even in a couple of hours. And so I want to concentrate on general aspects of the standards themselves that I believe stand out as needing to be rethought. The first is to connect the standards for mathematical practice with the content standards at each grade. Many mathematics educators stress that the essence of the Common Core lies in the standards for mathematical practice, the SMP. If you've attended sessions at conferences, including here, including this morning's session, you've all heard it often, ever since the Common Core appeared. But last January, I heard Bill McCallum speak about this. Now, Bill McCallum's the chief. He is le grand fromage of the Common Core. He was a panelist on 2 panels at the joint mathematics meetings. He said he knew that some people thought the standards for mathematical practice were the key things in the Common Core. But he asserted that is not true, because the standards for mathematical practice should be practiced regardless of the mathematical content. The essence of the Common Core, he said, was in the laying out of the content standards. That is, in the scope, sequence, and timing of those standards grade by grade. I agree with Bill's assessment of the essence of the Common Core, not just because he was one of the writers, but because of the relative importance given to the standards for mathematical practice and the standards for mathematical content in the Common Core. The standards for mathematical practice are detailed in 3 pages. They're the process standards. In contrast, the content standards occupy over 60 pages. I've ignored the repetition in the content standards. They actually occupy about 75 pages, but I'm cutting it down to 60. Now compare that with the principles and standards of mathematics of NCTM, where there were 147 pages devoted to the process standards and 152 pages devoted to the content standards, and you really see a major difference between the NCTM, PSSM, and the Common Core. The tension between the 2 camps, the camp of those who view the standards for mathematical practice as the key aspect of the Common Core, and those who view the content standards as the key aspect, is sometimes pushed into the background by those who argue that the key aspect of the Common Core lies not in the word core, but in the word common. That it's more important for the U.S. to have a common curriculum in order to prove mathematics education in the country than to quibble about aspects of the curriculum. And when people say common, they're talking about the content standards. They're not talking about the standards for mathematical practice. I think a revised standards needs to have a great deal of rhetoric and many examples per grade indicating how the standards for mathematical practice can be instantiated at that grade along with the content standards. Although these standards are called the Common Core, I think most teachers believe this core is larger in virtually every year than the curriculum it's supposed to replace. Some core. If the current curriculum is overloaded, what can you say about a curriculum that's even larger? Furthermore, all students are expected to learn the same core, and no country in the world keeps all students in the same curriculum through 11th grade. A revision of the standards needs to rethink the meaning of core so that it has practical applicability for all students. I think I understand the logic of the Common Core writers in this regard. I think we all believe that all students should graduate high school. It's also reasonable to believe that all high school graduates should be prepared for college. However, and this is a big however, being prepared for college does not necessarily mean that every student needs to be prepared for college-level mathematics. As a mathematics zealot, I want every person to understand the major ideas of my subject, but that doesn't mean that everyone has to be able to go in and work with these ideas in the same way that a mathematics major might. Let me give you some examples. Should all students be expected to compute with paper and pencil with decimals of any length? We can see that this is the intent by comparing the 6th grade standards, which I have down here at the bottom, with the 5th grade standards. In the 5th grade standards, there's a limit on decimal places that has been somewhat customary for the past few decades. 2 digits, decimals, that kind of thing. In the 6th grade, there is no such limit. Paper and pencil algorithms for multiplication and division of decimals are obsolete for most adults who will use calculators to obtain the answers if and when they ever would need them. And I need not tell anyone in this room that it takes a typical student months to learn these algorithms. A high school standard is that students should be able to divide polynomials. There is no way this is appropriate for all students. Again, there exists technology that can do these algebraic calculations with more speed and accuracy than students can. Steve Leinwan spoke about the same point this morning. Here, the Common Core authors missed the opportunity to bring the mathematics curriculum of the United States into the 21st century, and to some extent, they brought it back into the 19th. On the other hand, some of the STEM standards at the high school level should be for all students. Matrices and vectors arise in many kinds of data situations. They're part of the language of mathematics, and students should at least have seen them, all students. Should all students be taught the mathematics of lotteries? Yes, because they're ubiquitous in today's culture. They should know enough mathematics to at least be able to get to the mathematics of lotteries. Third was about evening out expectations. I don't know exactly how the work group and the writers worked to get the grade placement of the standards. One possibility is that they worked up from kindergarten and down from 12th grade, because the middle school curriculum is packed. In particular, the content expected to be mastered in 6th grade is massive. Here's the 6th grade overview. This is the overview. Notice the fundamental ideas. This is the big year for ratio. Steve Leinwan mentioned that. There's the expectation of computational fluency with decimals of any length, I mentioned just before. There is the extension of the arithmetic of fractions to deal with rational numbers. There are the beginnings of both algebra and functions. There's the geometry of area and volume. I estimate that there is about 45 weeks' work for a typical class to cover this content. But it's not just the time it takes. It's that so many of the ideas are fundamental. This was recognized by the writers of the Common Core, for at the end there is the following remark. Indeed, some of the highest priority content for college and career readiness comes from grades 6 to 8. This body of material includes powerfully useful proficiencies, such as applying ratio reasoning in real-world and mathematical problems, computing fluently with positive and negative fractions and decimals, and solving real-world and mathematical problems involving angle, measure, area, surface area, volume. The problem is, all of those things are in grade 6. Except for negative numbers. Everything on there is in grade 6. There's simply too much in that year. It's death. So you got to tell your grade 5 teachers, better get them grade 4. Tell the grade 4 teachers, do some of grade 5. Tell the grade 5 teachers, do some of grade 6. Otherwise, grade 6 is just going to destroy kids. And I worry. So kids will be asked to repeat grade 6 because they didn't get to some standard. And those are the kids who don't do so well in language arts either, usually. And they may be asked to repeat a year. And you see what I really worry. Another aspect of the unevenness of the expectations comes with the simplistic idea that the way to get students to algebra in 8th grade is simply to combine 7th and 8th grade into 1 year for those students. This recipe might have worked in the early 1980s, when grade 8 was just a repetition of grade 7. But it doesn't work in the 2000s, and because the expectations for the grade 8 have increased dramatically. And it won't work for the Common Core, which has still higher expectations for grade 8. The number strand in the Common Core reflects two views. One is antiquated and the other I believe to be simply wrong. The antiquated view is that children of the 21st century should learn about numbers in the historical order of their appearance, with the exception of 0. The wrong view is that children should not encounter numbers in class until they can be rather rigorously mathematically constructed. I say these views are reflected in the standards because I'm not certain of the extent to which they were consciously applied. Here's what I mean. Historically, fractions preceded decimals. And in the U.S. curriculum, that was the order of teaching until about 50 years ago. In other words, when I went to school around the time of Archimedes, this was the order. You learned fractions because there were no decimals. So you learned fractions first. The order changed because children today see decimals everywhere, with money, with times of events in sports, with results of searches on the internet, and so on. They see fractions in far fewer places. Consequently, not only because the algorithms for dealing with decimals follow closely the algorithms for dealing with whole numbers, but also because students have experience with decimals that can be applied to fractions, most curricula today do decimals simultaneously with fractions. Furthermore, converting fractions to decimals provides substantiation for the fact that different fractions can name the same number. But in the Common Core, operations with fractions precede operations with decimals, and indeed fractions are used to develop decimals. From a rigorous mathematics standpoint, this is fine, but that's college-level rigor that does not have to be foisted on young children. Historically, negative numbers appeared late, in the 16th century, just before decimals, and mathematicians found them more difficult to accept than decimals. So when I went to school, negative numbers were taught at the beginning of first-year algebra, in 9th grade, after the rest of arithmetic. But large numbers of curricula worldwide have shown that students can easily understand the uses of negative numbers in situations that have two opposite directions. They can understand that if you have $2 and you spend $5, you're going to be $3 short. So 2 minus 5 is negative 3. So some curricula introduce negative numbers in grade 2. But the Common Core does not want to introduce these numbers until grade 5, if reflecting a view that if something came late historically in mathematics, it must be more difficult than something that came early. Over the years, a few mathematicians, here's another example, have said to me that they don't like the fact that in many books, real numbers as opposed to those numbers that aren't really real. Real numbers have been described as those numbers that can be written as finite or infinite decimals, because the rigorous development of infinite decimals requires the study of limits, typically begun in calculus. Real numbers were not developed rigorously by mathematicians until the 19th century. So these mathematicians that feel that if something developed late in mathematics, it must be really non-intuitive, and the Common Core mirrors this view by ignoring infinite decimals completely. The infinite decimals are not found in the Common Core. These mathematicians have it all wrong. We get our intuition about real numbers not from the rigorous definition of a real number using least upper bounds, nested intervals, or Dedekind cuts. We get our intuition from the infinite decimals and the number line that comes early when the answer to a division problem is a repeating decimal. The Common Core recognizes the power of the number line, but doesn't take it far enough. Not one paper and pencil skill in algebra or arithmetic has been taken out of the curriculum. In fact, since decimals of all lengths and significant algebra skills are required of all students, the breadth of paper and pencil skills required of all students has increased. Not to mention that some of these students never ever took algebra. The Common Core writers were clearly worried about the early introduction of calculators. There's not even a single mention of calculators in either the narrative or the specification of content standards for grades K to 8, despite the fact that this is a curriculum that supposedly is to prepare students for work in a technological society. The Common Core ignore the world of today. They're 40 years out of date when it comes to considering how mathematics is encountered and used in today's world by everyday citizens. The standards speak often of the standard algorithm for doing an arithmetic operation. If we define the standard algorithm for an operation as the algorithm that is used by educated adults, and in particular, if we want fluency, by which is meant speed and accuracy, then the standard algorithms in today's world for work with multiplication and division of multi-digit whole numbers and decimals involve a calculator. And the most important skills lie in determining whether the answer one gets is reasonable, and in rounding the answer off to an appropriate number of decimal places. I should note, Steve Leinwan made a big point of this today, and I should note that Karen Fusen and Sibylla Beckman, two people who influenced the Common Core, have pointed out there is no arithmetic operation for which there is just one standard algorithm. They've written now extensively on it. It's the one thing in the Common Core that some of the authors are saying is wrong. Already, they're saying. Ironically, the standards do not seem to follow a line in their own standard mathematical practice regarding technology. And that is that proficient students are supposed to be sufficiently familiar with tools appropriate to their greater course to make sound decisions about when each of these tools might be helpful, recognizing both the insight to be gained and their limitations. How can teachers teach students to make sound decisions about the use of calculators if the students don't have them? You have to have them to make decisions. Despite a core that is much more than a full curriculum in places, I believe there are 8 serious, broad content areas missing from the core. First, quantitative literacy. We're in an age in which mathematical language and ideas are ubiquitous. Food packages list ingredients, recommended daily allowances to help people make wise decisions regarding what they eat. Financial matters involve more than the simple interest, tax, and discounts that are found in the grade 7 Common Core as applications of percent. Dealing with demographic and other data is important for understanding major issues of our day, such as global warming, population growth, and government spending. The importance of understanding the mathematics one encounters in everyday matters is described by such terms as numeracy, quantitative literacy, or financial literacy, and the standards wrongly assume that by being fluent with computation and understanding the uses of arithmetic operations, with which they do a very good job, by the way, the uses of arithmetic operations in the Common Core, really a nice job is done, but that a student would automatically understand its big applications. These matters do more than supply applications of mathematics and context for learning our subject. They help students understand the value of what they're learning, and they can help students develop robust concepts of number and operation. Mathematics for trades and other careers not requiring a college degree are huge and missing because the committee wrongly felt that the best mathematics for everyone, and I repeat, for everyone, is the mathematics that a student taking college mathematics needs to know. There is almost no attention given to data before grade 5, except a strange obsession with data that comes from measurement of lengths in objects. I wonder why the writers did not adopt the standards following the well-known and carefully written American Statistical Association guidelines for the assessment and instruction of statistics education, the GAISE, what are known as the GAISE, GAISE standards. They were published 2 years before the Common Core. They're gorgeous. If you've never read them, they're incredibly good. Actually, the assumption is that the best mathematics for everyone is more narrow than the mathematics needed for college. It's the mathematics needed for calculus and statistics. And this is a big thing in the Common Core, that they do have statistics in there. but only math and statistics. There is disregard for the discrete mathematics that's fundamental in computer science, even in the extra mathematics for those in high school who will take college mathematics, those standards that I've been calling the STEM standards. The STEM standards designed for our best students have a major weakness. There's no applications other than probability. In fact, as I've mentioned, some of those applications, like lotteries, should be for all students. They should be in the core. It's amazing that the metric system, with its connection to the decimal system, is not part of the core, though metric units are mentioned in some examples. I believe this is another consequence of the archaic approach to decimals, in which there is ignorance of the fact that students see decimals everywhere, from money to measurement, yet the discussion of decimals is made dependent on fractions that are far more difficult and less in the world of students. The word infinite never appears in the Common Core even once. Amazing. Are we not to teach students there are infinitely many integers? What about the end behavior of functions? There's no discussion of infinite decimals, so what are students to learn about pi? The only mention of limits is in connection with informal arguments about the areas and volumes of curved figures. The phrase infinitely many appears twice, both times to describe how many solutions there are to inequalities. There are infinitely many solutions. First graders can understand that there are infinitely many integers because they can see that if there's a largest number, then there's a number one larger. That was part of the curriculum in the PBS program, 3-2-1 Contact, many years ago. There's a great song about that in that program. Now let's turn to the fourth part of this presentation, the changes that should be made in the testing program. The problems with the Common Core could be ignored if there were no testing program based on them. Then the weaknesses of the Common Core would be somewhat like the weaknesses we can find in almost any program that's available. But the testing program is so flawed that it's going to be a disaster. There are problems with the questions that are being proposed and the number of tests, and these problems are compounded by what we already see will be the interpretation of the disastrous results that are bound to occur. What kinds of questions are students being asked to solve? On the PARCC website, we're in a PARCC state, folks. By the way, no states have seceded from the Smarter Balance Standards. Just so that you know, only PARCC. Aren't we? Isn't it great? There are now 21 sample problems on the PARCC website. Here is a sample item for high school that is identified as seeing structure in a quadratic equation. Maybe, how many of you have seen this item? Okay, so I'm not making this up. Solve the following equation. 3x minus 2 quantity squared equals 6x minus 4. I'm a student. I see the structure. The right side is twice 3x minus 2. And, I can divide both sides by 3x minus 2, and I get 3x minus 2 is equal to 2. So I get 3x equals 4, and x is equal to 4/3. I substitute back in the original equation, and it works. The only problem is I haven't done the question correctly. I saw the structure, but I blew it. I've forgotten that I cannot divide by 3x minus 2 if 3x minus 2 is equal to 0. And when 3x minus 2 equals 0, x is 2/3, and that's a second solution to the equation. I've lost a solution by dividing both sides by 3x minus 2. If I don't see the structure, what do? I expand the left side to obtain a quadratic, and then I add negative 6x plus 4 to both sides, and I get an equation 9x squared plus 6x plus 8 equals 0. I use the quadratic formula, and I get two solutions, 2/3 and 4/3. So if I don't see the structure, I might be more likely to get the correct answer. This question is supposed to be there to see structure. But you're better off if you don't. The addition and loss of solutions to equations is typical pre-calculus content, 12th grade mathematics. This question is what you discuss when you are teaching about extraneous solutions to equations. It's the kind of question found on math contests because it's so tricky. It does not belong on a test over the Common Core. Questions like these survive on tests because a percentage of students between 10% and 90% get them correct. So they're viewed as not too difficult and not too easy, and because the tendency is for the top-scoring students, more top-scoring students to get them right than bottom-scoring students, so they get a reliability, nice reliability. Sure, how do you get to be top-scoring? You get these questions right. But the face validity of the question and its relationship to the curriculum need to be given at least as much weight as in viewing the item. A second question, sample question, is the following 6th grade item. It's called slider ruler. It's a long item, so I can't show it all on one slide. Here's the stem of the item. You can see the 2 rulers are, how many of you have seen this one? Oh, fewer. Oh, are you lucky? Because you can see it here. The 2 rulers are given. The student is to use a slider to find the relationship between the number of inches, the top inch ruler, and the number of centimeters in the bottom. The question is to select all of the statements that accurately represent the relationship between the number of inches and the number of centimeters. Here are the statements. There's 6 statements. Do you think this item's a little tricky? You think so? There is evidence that it is. And we don't have to pretest the item to know this, because this item is directly related to a famous problem from the research of John Clement, Jack Lockett, and George Monk in 1980. Here's their problem. Write an equation for the following statement. There are 6 times as many professors as students at the university. Use S for the number of students and P for the number of professors. Percent of correct answers from the 2 samples. 150 calculus level students. This was given to college level students. 63% got it right. Of college level students, 43% of non-science majors. Those calculus levels, these are people who need it, they have to take calculus. The problem is in a sample for 6th graders in the Common Core. 6th grade. Now, it's also been reported that difficulty, that's at the bottom here, difficulty in solving this and similar problems is highly resistant to remediation. In other words, even trying to teach kids what the right answer was didn't result in much better performance because it's so tricky. Moreover, here, go back to this item. It presents even worse. The professor's students is easy compared to this one. And the reason it's easier than this one is that 1 inch equals 2.54 centimeters. So you are sucked into thinking that 3 is correct. The third one down here is correct, that I equals 2.54C. That's not right. Now, you have a slider. Does the slider help or does it hurt? Certainly it will cause students to spend more time on the item, and it may cause students to wonder why they're supposed to learn something, or whether they're supposed to learn something from the slider. And if they thought one thing one time, maybe the slider is supposed to change it so that they're wrong. I mean, they're completely confused. You're going to get random response. The kind of question is totally inappropriate, but it's given a sample as to what to expect from PARCC. It should be obvious. There shouldn't be tricks or contest problems. The questions on a test of the Common Core should be appropriate to the understandings that a student should be expected to have at the grade at which the test is taken, not the understandings that a typical student acquires only after years of experience with the content. The PARCC website refers the reader to a large collection of items created by the Dana Center. And the list of contributors to these Dana Center items is impressive. It includes past presidents of NCTM, NCSSM, and other well-known figures. And the subject matters of the items are quite appropriate, unlike the samples on the PARCC. But the items, one after the other, have their own difficulties. Most are as much measures of reading comprehension as they are of mathematics. Many have so many parts that they measure a student's determination more than mathematics, and another have confusing directions. Smarter Balanced also has a large number of sample items available. There are difficulties with a few of them, but I can't comment on them because I couldn't find the particular grade level at which any item was to be given. No problem here in Illinois because we're a PARCC state. The questions on a Common Core need to be rigorously pre-tested. For 10 years, I was a member of the National Assessment Mathematics Test Committee that edited the National Assessment Tests. I considered myself very experienced and knowledgeable, not only about the curriculum, but about setting test items for students. It was amazing for me to see at every meeting of this committee that many people found problems I didn't discern. Problems with question wordings, with bias of one kind or another, with interpretations of how students could get the right answer for the wrong reason, or the wrong answer for the right reason. Very few questions survived intact. I think very many of the sample items I viewed on the internet from PARCC would have made it through. Very few. Kentucky was the first state to adopt the Common Core, and last year it became the first state to give an assessment based on the Common Core. In grades 3 to 5, the percent of students that were considered proficient dropped from 70 to 47%, grades 6 to 8 from 65, 41%. Grades 9 to 12, well, not too much of a drop, just 46% to 40%. What was the reaction of the Kentucky Education Commissioner? He said, we knew the scores were going to drop, but this is the right thing for our kids, for our schools. In my opinion, he's happy the scores dropped because it justifies the Common Core and all the money they're spending on Common Core testing. In fact, if the scores increased, he probably would have complained that the test was too easy. The Education Week article writer from which I got this interviewed Douglas McRae, a retired assessment designer who helped build California's testing system, and McRae pointed out what most of us know. When new tests are introduced, states can expect scores to drop. When you change the measure, change the test, then you interrupt the continuity of trend data over time. That's the fundamental thing that happens. This quote is disturbing on two fronts. First is the expectation that scores will fall. If it's a new test, what do they fall from? In Kentucky, it was the percent of students scoring proficient or higher, but the earlier test was completely different from the Common Core test. Would students now score better on the old test? If you don't give the old test, you have no way of knowing. It's important that we keep track of how students would do on earlier measures of performance because our successes have been lost on the Common Core rhetoric. Although it's perhaps the major weakness of our educational system that the mean scores of blacks and Hispanics on national assessment at grades 4 to 8 are about 2 years behind the mean scores of Asians and whites. The mean scores for all groups have increased significantly since the 1970s on the longitudinal study and since the 1990s on the short-term study. Here are some of these increases. An increase of 14 points on the NAEP is considered about equivalent to a year's study. In the past 20 years, we have had an overall increase on the national assessment of about the equivalent of 2 grades at 4th grade, from 213 to 241, and about 1.5 grades at 8th grade, from 263 to 284. The mean score on the SATs increased from 501 in 1990 to 515 in recent years, and it's now leveled off. The mean score on the ACTs increased from 19.9 to 21.0, despite the increase in the number of ACT test takers, all doubling, and states like Illinois now requiring the ACT of everybody instead of just those going to college. If there becomes some move to change these tests significantly due to the standards, and it seems to be that there will be with the SAT, a revised standard should call for the reinstatement so that we can really see whether the Common Core has raised achievement. Also lost in the Common Core rhetoric is the extraordinary success of a nationwide program that involves our best students, AP Calculus. I was in Japan earlier this year speaking to Japanese mathematics educators who are often in the United States. People from Japan who probably know the most about our system of the Japanese. And showed the following data. 1982, 6% of our high school graduates took calculus. It's now 18% in 2009, and it's increased since 2009. Now it's probably somewhere around 21%. Number of graduates taking the AP Calculus tests, taking the test, has increased from 32,000 in 1982, 156,000 in 2002, 283,000 in 2012, the last year for which I could find the data. Since 2007, more high school students have taken calculus each year than college students. And the gap continues to increase. The response of one of the Japanese educators was, "I had no idea. We thought there were no good students in the United States." And so you'll have to excuse my departure from the Common Core to give you this rhetoric. With so many students taking the test, you would think that the percent of students obtaining the highest grades, excuse me, you would think that the percent of students obtaining the highest grades would decrease. But through this period, those percentages have increased on both the A, B, and BC forms of the test. In 1999, 38% of A-B test takers scored 4 or 5. In 2012, it was 42% of the test takers scored 4 or 5. In 1999, 79% of BC test takers scored 3, 4, or 5. In 2012, 82%. And look at the increase in number of students from 1999. It's in red. In the A-B test, the 5s increased from 19,000 to 67,000. Much greater percentage. More 5s than 4s now. It used to be more 4s than 5s. And on the BC test, from 11,000 to 47,000. The Common Core does not mention calculus in high school. Its rhetoric is, the high school standards specify the mathematics that all students should study in order to be college and career ready. Additional mathematics that students should learn to take advanced courses such as calculus, advanced statistics, and discrete mathematics is represented with a plus. You know that if you looked at the Common Core. This is understandable in a set of standards for all students. But it's not clear what will happen with this population, this high-performing population with the Common Core. Before the Common Core, there was not much new content introduced to grade 8. So a strengthened grade 7, followed by teaching algebra or an integrated grade 9 course in grade 8, was much easier to cover. Any weaknesses in background would be covered by the higher expectations in the high school courses the best students take. I worry that putting all the pressure on the middle school, coupled with a greater number of tests that can serve as filters, will decrease the number of students who finish what has to be considered the greatest success story of the recent past in school mathematics education. Just so you know, I have about 3 more minutes if you bear with me. Last, reduce the number of tests. For well over a half century, many schools and school districts have given elementary school students standardized tests every year. These tests have been used primarily in 2 ways. They tell teachers who are the better prepared students and who are the lesser prepared. And they are often used as one indicator to sort students into advanced, regular, and remedial classes. Although most of these tests provide detailed information about strengths and weaknesses a student has in various areas of mathematics, I think that in most schools that detailed information is ignored. Should we expect more from PARCC or Smarter Balanced? I doubt that more is possible. Because there are tests in language arts and mathematics, the 2 most important subjects in the elementary school, and because students who score poorly in one of these areas tend to score poorly in the other, I foresee huge numbers of students being held back, whereas without the tests, they would remain with their peers. The research evidence is that holding students back does not increase performance, so we will have more students who are older than their classmates, and these students will be more likely to drop out. No country in the world gives high-stakes tests every year, yet the Common Core tests will be high stakes, with schools ranked by their results, and in some places, teachers ranked as well. If those who conceptualized the Common Core really wanted to emulate Singapore and some other nations of East Asia, then they would have had only 2 tests, one at 6th grade and one at 9th grade. A second edition of the Common Core should be honest with the mathematics education community. It should indicate which ideas that are being proposed are untested and which ideas constitute a policy different from those of other countries with whom we are compared. But we have to be diligent. Some people in high positions are test crazy. In Texas at present, students must pass 15 tests in order to graduate. I believe most, if not all, of these tests are statewide course tests. A test over algebra, a test over geometry. People have protested that this is too much testing, but education leaders are opposed to a reduction. Maybe this is why Texas didn't join the Common Core. There were too few tests in the Common Core. You may not agree with my opinions, but I hope that I've at least spurred you to think that we should be starting now to think about what a revision of the Common Core would look like. Thank you very much for listening. What?
It was sharper the last time. You've typed